Hey everyone, and welcome to our lecture on Chapter 5, Managing Hardware. In this lecture, we're going to talk about how we can learn more about the CPU, identifying motherboard capabilities, sizing out power supplies, understanding disk issues, managing displays, handling USB devices, and managing drivers. And all of this is going to be in the context of from a Linux-based operating system. So how can we learn about our CPU? Well, first we need to understand that there's different CPU families. So the ones that we're probably most familiar with are these three right here: x86, x86-64, and ARM. So what are the differences in these? Well, x86 is a 32-bit processor. So these are the processors that Intel makes and AMD makes and that we used in the 90s and early 2000s. They were all x86 based, and you could still get some x86 based processors that are strictly 32-bit, but nowadays we have these x86 64-bit processors. So it's a 64-bit extension on the 32-bit instruction set. All right, it just allows for the data that we refer to and the operations or instructions to be longer, or in this case, 32 bits longer, right? And then the other one is ARM. And where we see ARM used a lot is in mobile. So you probably have an ARM processor in your cell phone. You may have a uh, what are they called? The Microsoft Surfaces, the RTs. Those have an ARM processor. Tablets have ARM processors. A lot of embedded devices do. And the big allure of an ARM-based processor is that it's much more efficient with the power. Okay, so that's why we see them in mobile applications, because we're typically reliant on a battery in that case, and we're not plugged into a wall or something like that, where we don't really have to worry about power. Additionally, just a little bit more, the x86, x86-64 is known as a CISC architecture. So that's complex instruction set computing. And then ARM is a different type of processor known as RISC, or reduced instruction set computing. So what this basically means is that if you think about the whole set of instructions that you can use in an ARM-based processor, is smaller than the set of instructions that we can use in an x86-based processor. So really, there'll be some instructions in x86 that might correspond to a couple of instructions in ARM. And the reason being is just because we need to uh, use multiple instructions to do that complex task that might just be one instruction in a CISC-based architecture. All of these guys, though, can run Linux. All right, so how can we identify our CPU? Well, there's a few things we can do. So let's jump over in Ubuntu and take a look. All right, so the first thing I want to do is let's jump into the terminal. So I'm going to open up the terminal just by searching for it here. Okay, once I have it, I'm going to go ahead and lock this or pin it to the bar so that it's always there. The first thing we'll look at is this uname-a command. So this gives me a little bit of information about this particular installation of Linux. It tells me that the name of the computer is Ubuntu-VM. Here is the kernel version that's being used. We have, I would assume this is the date that the kernel was compiled. And then we also have the architecture. So you see here x86 underscore 64, that should look familiar because we just got done talking about that. So we know that this particular version of Linux was compiled for x86-64, so we can assume that the processor is also x86-64 because it is running successfully. Now there's some other commands that we can use to get a little bit more information. So looking at the next one, let's look at lscpu. LSCPU will list out information about the CPU. Okay, so let's make this a little bit bigger. And it looks like I only have one processor in this particular VM. I could go and add another one and we would see two listed here, but that's okay. Let's look at some of the other information that we see. So the architecture, x86-64, we already assumed that from the last output. We see that the op modes, or the operation modes, what sort of instructions can it take, are 32-bit and 64-bit instructions. We also see the byte order, so the way that the bytes are stored in memory is something called Little Endian. We don't necessarily need to worry about this too much, just realize that there's two kinds of Endianness, and one of them's Little Endian, the other one's Big Endian. For the most part, we'll see Little Endian in operating systems, and we usually see Big Endian in networking. So how many CPUs are there? Just one. Let's see, what else is interesting here? Threads per core, we're only seeing one. We find out some other good stuff like the vendor ID, so genuine Intel. We know that this is an Intel based processor, and if we go down a little bit further we can look at the module name and see that this is a Core i5-4258U running at 2.4 gigahertz. Okay, so that's cool. I could look up information on this processor if I wanted to now that I've been given the model name. And we can see the speed of the processor again. So that was already listed here, but in a field by itself is 2,400 megahertz or 2.4 gigahertz. And then we can see some information about the cache. So cache can be interesting. We see a few different levels of it. So we have a level 1 cache, and you see that one of them's D and one of them's I. So the level 1 D cache is just for data. So data would be something like variables for a program. Essentially anything that's not an instruction is data. And instructions, as you can probably guess, go into this level 1 I cache. So we have 32 kilobytes of both of those. Moving one level out, we have a level 2 cache of 256 kilobytes. And then we have a level 3 cache of 3072 kilobytes. All right, so we got three levels of caching going on. Why, right? When it comes to actually running programs on the processor, so we have, let's say we have a processor, and a processor has a certain amount of registers, which are very fast memory locations inside the processor, but they're not big. So they're only the size of the word in a computer. So they're either 32 bits or they're 64 bits. So we call this a registers. They're usually going to be 32-bit or 64-bit. And then sort of on the other side here we have our RAM. We're familiar with RAM. We allocated RAM for our VMs. We usually have somewhere along the lines of 1 to 8 or 16 or 32 so gigabytes of RAM available. And as we need things in these registers, so as we need instructions to be moved into the registers, as we need data to be moved into the registers, we need to go out to RAM to get those. And from RAM, they get put back into our registers. Now, to speed this up, because remember I said that these guys right here are very fast, right? The registers are very fast. The RAM is also fast, but it's an order of magnitude slower than our registers. So let's differentiate here. Let's say very fast and fast. So in between to sort of optimize this process, we create a couple levels of caching. So let's simplify that level 1 DNI into just a level 1 cache. Then let's have a level 2 cache and then a level 3 cache. So, rats, I was hoping that would erase. Oh, that's okay. Alright, so as we need something in these registers, we tend to need the same thing a lot, right? If we're working on data, we're like keep adding something to something, then we need to keep that one thing around that we keep adding to. So as we need things in registers, first we go and check the level 1 cache and we say, well, do you have memory location such and such? And we'll get something either called a cache hit or a cache, if I can spell right, a cache miss. So if we get a cache miss, then what it's going to do is it's going to go and look in the level 2 cache and it's going to say, all right, do you have memory location such and such? Well, if it doesn't, then it's going to be a cache miss. And it'll check level 3 cache and ask, do you have memory location such and such? And if it does, let's say that the value is 8, then what it's going to do is it's going to move this 8 into level 2. Oh, I don't know what I'm doing here. Let's see, make that an 8. And then it's going to move that 8 into level 1. And then it's going to ultimately move that into one of these registers here. So that the next time that we go and we say, okay, maybe we've overwritten this register with some other data. Now we need to go back and get that memory location again. And just for the sake of simplicity, let's say that we haven't changed the value in that memory location. So we've only read it. Well, we can go back to the level 1 cache and say, do you have memory location so-and-so? And it'll say, yeah, I do actually. That value is 8. And it'll go ahead and move that right into a register. Okay, so we have these cache hits. A cache hit is when we find what we're looking for. A cache miss is when what we're looking for is not in the cache. And we just keep checking the next level, until ultimately we run out of levels of cache to check and we have to grab that value out of RAM. So we have something like that 8 sitting right here. Alright, so there's a lot to do with caching, and we could talk all day about caching and the architecture of processors, and that's not really the scope of what we're doing here. I just wanted to make sure that you understand why these caches exist, what's the significance of them, and I guess I should mention that these guys are also very fast memory access. It is also very expensive. So since it's expensive, that's why we don't have much of it, because I mean, look at what we're dealing with here. 64 kilobytes plus 256 plus 3 megabytes. We have less than 4 megabytes of cache. But that's because it's very expensive, and RAM is not nearly as expensive as cache, so I can have a lot more RAM. It's not, you can buy, I want to say I was looking at like 16 or 24 gigabytes of RAM the other day for under $200. Of course, that's for a desktop. But still, it illustrates the point that RAM is a lot cheaper than cache. Okay, and there's one other spot that we can get some information for the CPU, and that's in the proc file system. So, proc file system exists in a folder /proc, and it's a virtual file system in that those files that we see there don't actually exist. Now, I know we haven't talked much about command line interaction just yet, but I guess now's a good time to introduce a few commands. So let's change directory to the proc directory. So we can see that my shell prompt changed here to let me know where I'm at in the file system. If I do an ls here, we can see a bunch of files. So all of these guys in blue, these guys are running processes, and we could look at peek in there and see what's going on. Like 1 should be init. It's not going to let me see everything because I'm not running as root right now. But we can look at something like the command line and we can see what is it running. So that's the command that's actually being ran. And what I'm really trying to show you here is the proc file system, these are not real files. These files are virtual. They don't actually exist. They come from the kernel. The kernel is exposing this data to us. And one of the files, let me just clear this out and do an ls again. One of the files is CPU info. All right, so we can get a little bit of information there. So let's cat, and what cat does is it dumps a file out to the screen. It's actually short for concatenate. It's probably one of those words that you heard thrown around in a programming class. But it concatenates a file to the the screen, and we could actually put multiple files together and have them go out to the screen. Let's look at this basic use case though. We got the CPU info file, and we want to cat that out to the screen so we can look at it. Okay, so if we run that, this actually looks really familiar, doesn't it? It looks a lot like LSCPU. Again, looking through here, we have like a process identifier. So, in computer science, most things start at 0 is where we start counting. So that's why that's a 0. We see that vendor ID again. We know this is an Intel. We could look up what these map to, but it also tells us the model name. So that Core i5-4258U. Some information about it like stepping and the clock rate, the cache size. Notice it doesn't get granular like the LS CPU. It's not showing us the cache size for L1 and L2. Does it do FPU? What all does it support? That's what these flags are down here. So you can look up what some of these flags mean, but they're just capabilities of the processor. Look at hypervisor being one of those capabilities. What's the takeaway from this? We got a few different locations that we can look for CPU information. Keep in mind that they're not all going to return the same stuff. This one really just told us the architecture. This one probably told us the most detailed information because we got that level 1 and level 2 cache. And there's probably a few things that I didn't realize that CPU info shows us that LSCPU doesn't. Alright, so identifying motherboard capabilities. These are plug-in interfaces for like slots. So if we have extra slots or sockets for our CPUs, different slots for RAM, we have to plug those in somewhere on the motherboard. We can add things to motherboards using PCI connections, so peripheral component interconnect. That's a good way to add other cards like USB 3, FireWire, more network connections. You get kind of obscure with some of the hardware and have something like maybe InfiniBand or something like that. It's also got connections for hard disk drives or persistent storage. So SATA connections or the older parallel ATA connections or PATA connections. Back panel connectors for external interfaces for USB devices, keyboards, monitors, and so on. And then, of course, there's usually something on the front panel of a computer, particularly desktop computers, and it may have some USB connections, sound connections, microphones, stuff like that. Okay, so how can we find out about this information? Well, there's another command called lspci. Remember PCI, Peripheral Component Interconnect. This will tell us about some of the things that are plugged into our motherboard. So you'll notice that this ls command is sort of a family of commands, and really it doesn't have like this disjoint from the ls command, and this is different from the ls CPU command. But ls means to list something. So the way that you can remember this or keep this in your head is that lspci is to list the PCI components. Let's come back over here. We can type clear and enter, and that'll get rid of that stuff. And let's type in LSPCI and see what we get. Okay, so this can help us derive a little bit of information, especially useful if we got some new hardware and it's not working automatically. So maybe we plug it in and we can get it to list in here, but it's not working as we expect it to. Then we can use this to Google maybe the model number, the vendor, and find out what we can do to fix it. So let's see if there's anything cool in here that I can point out. So here's the SATA controller. SATA controller, again, is for mass storage or persistent storage. We have a graphics adapter, so that'd be like a graphics card, and of course this is virtual because we're in a VM. Where is, I guess we have a USB controller here. Another USB controller. So this is probably from, I have an Apple monitor in here and it's got USB on it, so that's probably where that's coming from. We saw the VGA controller. Oh, here's the Ethernet controller. So this is where the network comes from. We can see that that is the hardware that's being emulated by VirtualBox is an Intel 82540EM, and that's a gigabit Ethernet controller. So without even looking anything up, I know that this Ethernet controller is capable of gigabit speeds. And if I was having trouble with it, I would just Google probably this string right here and my distribution to see what I can find out. Sizing your power supply. First off, what is the purpose of a power supply? What does it do? We had talked about this in the computer hardware video a little bit, but what a power supply does is it converts AC power to DC power. All of our electronic devices don't run on AC power, so we have to do that so that we can give it the power that it needs. There's a couple different types of power supplies. We have internal power supplies and we have external power supplies. An internal power supply is like we saw in the slides for the computer hardware lecture. It's typically like a big box and it's got a power cable that comes in from the wall, and then it's got some power connections that come out this way to power things on the motherboard. Okay, so this is a power supply, and it's probably got a big fan or something right here to cool it down. So this would be an example of a internal power supply. An external one is something like what we're more familiar with laptops. We have this little like power brick, and one side of it goes to the wall, the other side just plugs in nicely to our laptop. You're probably seeing why I'm not an artist. Okay. Another type of external power supply is like what we see with cell phones or tablets. We have those little, sometimes called wall warts that plug in right here, and it's like a square with USB sometimes, and just a cable going out of it that plugs into something like our cell phone. Now, what do we want to be careful about with power supplies? We want to make sure that it's rated to distribute the amount of power that we need. So different components, and especially if we start buying aftermarket components like a graphics card, is going to say I require a certain amount of wattage. And we just need to make sure that based on the wattage that it requires and the wattage that our motherboard requires and the wattage that our CD drives and hard drives require, that our power supply is actually capable of doing that. Another example, let's say using an external power supply, you may have heard of a device called a Raspberry Pi. It's just a tiny little chip, and it's got other chips on it, and it's actually a whole computer just on a chip. It's sometimes called a system on a chip, SoC, and it takes the power supply from the wall, basically one of these little wall wart things, and it requires 2 amp output. So without that 2 amp output, you might run into some issues, and I've used some power supplies before that are only half amp or 1 amp, and as soon as you plug in too many things to the USB ports up here, the whole thing shuts off because it didn't have enough power to power the processor on here and all of the other components, as well as provide power to those USB devices like a keyboard and a mouse and so on. Okay, so what sort of things come up with disk? We have two different interfaces for disk, and the first one is a legacy interface called PATA, and that is a parallel connection. And then we have SATA, which is newer. Oh, let's see, that is a serial connection. So here's the idea between the two. Um, and I guess just to mention here, PATA usually uses a ribbon cable. So it's like a cable that plugs in down here, and then it's got like 40 wires coming out of it, and then those wires plug into the back of a hard disk. So, and this cable is usually called an IDE cable. So IDE cable. Now, you would think that this would be faster, and it's actually not. When we send data down this, let's say just for simplicity, we're sending 40 bits at a time, and we can send 40 bits using this IDE cable because there's 40 wires. So we just send 1 bit down each wire, 1 0 or 1 1 down each wire, and they all have to get there at the same time. Okay, so that creates an issue with throughput or bandwidth. We can only send it so fast because they all have to get there at the same time. The SATA, on the other hand, uses a much smaller connection because it's serial. It's one after the other. It sends 1 bit at a time. So we got our connector, and this connects. Both of these would connect on the motherboard somewhere, and then it's just a thin little cable, and that connects right into the back of our hard drive. So it's sending 1 bit at a time, just 1 0 or 1 down that wire to the hard drive. Um, and this turns out to be quicker because we can actually send these bits faster, and we can get 40 through this wire quicker than we would just by sending 40 in parallel to the hard disk drive. Okay, so what's the takeaway? PATA's old. We don't see that as much. SATA's new. And this is what we commonly see in motherboards nowadays. And there's some other connections that are coming out, like M2 connections. You can also find little PCI cards that have SSDs on them, and that's another way that we can hook our hard drives up to the motherboard. But typically, it's through one of these cables, a SATA cable or a PATA or IDE cable. Okay, so partitioning a disk. There's a couple ways that we can partition a disk. And what partitioning is just like if we take a room and we put a wall up in the middle of it, we partition it. We can take a whole hard disk and we can break it down into little pieces that the operating system sees as its own sort of hard disk, right? It's viewed as a partition, but it's like an encapsulation inside that disk. So let's do a simple example. Let's say that our whole hard disk is 100 gigabytes. Then we might have a boot directory that's only, let's say, 1 gigabyte, and we might have a root partition I shouldn't really call this a directory. It would be the boot partition. And then we'd have a root partition that maybe needs to be, let's say, 20 gigabytes. And then we need a swap partition. Let's say that that's 4 gigabytes. So the rest of this can be given to our home folder. And our home folder is where stuff for our user gets stored, like documents and uh, applications that don't need to be available to the whole system. We can install those into the home folder. So what do I have left over here? I got 4 plus 20 plus 1 is 25, so that works out nicely. I can have a 75 gigabyte home partition. So the OS files would get installed into root. The boot files, as you can guess, these are just needed to boot up, would just be stored here in the boot partition. And then swap, I think we've talked about swap, but when we run out of RAM, physical RAM that we can put stuff into, then we start paging it out or taking memory out of RAM and putting it on the hard disk drive, because we're not using it at the moment, and we have other applications that need to use the RAM. So we start putting that into swap so that we can open up some space. Okay. So what we just looked at right here is known as a partitioning scheme known as master boot record. It's also called MS-DOS partitioning. It gets its history from MS-DOS, is where it was first created. Sometimes it's also called BIOS partitioning. And it supports disk up to 2 tebibytes, so 2 terabytes here in size. And it has a couple different partition types. So we can have at most 4 primary partitions. We can have 1 extended partition, and we can have 11 logical partitions. Okay, so what we see up here is we have a primary partition, another primary partition, and then we have this extended partition, and inside the extended partition is where our logical partitions reside. So these guys, swap is logical, and so is this home partition. Now, as you can imagine, having this 2 terabyte limit, we've already got drives that are bigger than that. We have 4 or 5, 6 terabyte drives now. So another partitioning scheme was created, and it's called GPT, and it's based on globally unique identifiers. So it is a globally unique identifier partition table. That's what GPT means. And it supports disk up to 8 zettabytes in size. So that is a very big hard drive. We haven't reached that yet, so we're not worried about that just yet. So who supports what, right? Linux supports MBR and GPT. Windows BIOS, okay, only supports MBR. So if you're running Windows on an older laptop, older desktop, you probably have just regular old BIOS firmware, and it's going to have to use MBR. But if you're running Windows and you have UEFI firmware, even if you're running legacy BIOS, so if your processor, your motherboard supports this UEFI firmware, then Windows in turn can also support this GPT table partitioning style. Alright, so there are some software out there that'll help us partition these disks, and one of them is fdisk, and then there's libparted, and GPT fdisk or gdisk is also available. I tend to like to use, especially when you're just starting off with Linux, a particular partitioner called gparted, because that gives us a GUI to go with it. Oops. Let's see if gparted is installed. Of course not, but it'll show me how to do it. So I can type in this command right here and we'll get a copy of gparted and just take a look at it. Okay, so we just reached out to one of those repositories so that we could download the gparted software. Now that that's done processing, it's already installed, so we can just type in gparted and press enter. Well, it's going to ask for root privileges, so let's put sudo in front of that. And here's gparted, so we can see how the installation laid out our disk. We can see that I have a disk up here that's 20 gigabytes big, and that disk is known as SDA. So all of our disks, we can find them in the /dev folder. SDA is the first hard drive. And we can see that it's got some partitions here. So we have SDA1, which is an ext4 system. So that's the file system. We can see the size of it is 18 gigabytes. So they have another 2 gigabytes used for something else. We can see that here. We have an extended partition, and inside of that extended partition we have swap space. So that swap is the other 2 gigabytes there. So you probably notice a naming scheme taking place here. We have uh, disk, disk device 1 and disk device 2. Once they're detected and connected to the machine, the first one shows up at SDA, and then SDB, and then SDC, and it just goes on through the alphabet. As we start partitioning these devices, we put numbers after it. So SDA1 is the first partition on disk device 1, and /dev/SDA2 is the second partition on disk device 1. Right, so it's a pretty easy naming scheme, and it helps us to be able to understand, what we're looking at when we see these file paths like this. So I guess I didn't have to install that. We actually have a screenshot here of gparted showing us how we can partition a disk. And a nice thing about gparted is that it's a GUI, so we can come in here. I can't really do it on the SDA drive because the SDA drive is the one that's currently being used, so we can't resize things. But if this wasn't being currently used, we could right click here and resize this. I could make it smaller and create more partitions, or if I had some free space, I could even extend this and make it bigger. So it is possible after these partitions have been set up to go back and sort of modify them. All right, so what kind of issues can we have with the file system? I guess the first thing that's important to know is that Linux uses a root file system. So if you're coming from the Windows world, you're probably familiar with the notion that your main hard drive is the C drive, right? Well, the C drive in the Linux world is this slash. It just means the root of the file system, the base of it. And then everything else is underneath the root file system. So we have directories like the etc directory and the home directory, and then things exist under the home directory. Like I might have an account on the computer and I might have a directory underneath there, and in there's where I can put some of my files, like I don't know, lab.doc. So we need a system or a way to store data onto the hard drive, and we use file systems for that. So many different types of file systems. We're really only going to see a few. There's this ext file system, and it's gone through a few different versions. So we have ext2, and then we started adding journaling to it. So we have ext3 and 4, and journaling just sort of keeps track of the changes that have taken place before they actually get finalized on the disk, so that if we ever lose power or something, you'll see that your data gets restored then. So we don't end up with very much corrupt data at that point. There's some other file systems out there, and each one sort of has its own benefit. There's RiserFS and JFS and XFS, ButterFS, and some of these are better with big files. Some of them are better for media. As far as just standard use file systems, the ext file system is what we see used the most. In fact, I believe as we were looking, we saw that in gparted, just bring this up one more time, that this is an ext4 file system. So that's the default for an Ubuntu install. Hey, there's some other important non-Linux file systems out there too, like FAT, File Allocation Table is what that stands for. And the most popular version that we probably see is either Extended FAT or FAT 32. So this is a legacy file system that was used in earlier versions of Windows. Shoot, all the way. You can still format FAT disk in Windows. Nowadays, Windows is using this NTFS file system because it supports larger files and larger disk sizes, whereas FAT had limitations on it. And I believe at one time it was limited to like 2 gigabytes, or there was a point in time where it was limited to 32 gigabytes. And just as hard drives got bigger, they had to come out with other versions of the FAT file system. So there are other ones out there. There's FAT 16, there's FAT 32, and like I mentioned, exFAT, extended FAT for bigger file sizes. HFS, the hierarchical file system, and HFS Plus, these guys are used in Mac. So let's see. This is Windows. This is Mac. So I don't know much about the HFS file system. I know that this is the older one, right? And then HFS Plus is sort of the evolution of that that's currently being used. And then we have these guys down here, and these are file systems for CDs slash, I don't know why I drew a B there, DVD. So ISO 9660 is sort of the legacy CD file system. It has limited support for file names. For instance, by the standard, file names can only be 8 characters long. So if you end up with a bigger file name than that, it just kind of gets truncated. There are some there's some extensions that were written on there, like Juliet, that allow for longer file names, but the new standard that they're trying to use is UDF, and that allows for larger file names, and it's just a file system for CDs and DVD drive, or not drives, but for those that medium. Okay, so as we take a disk and we plug it into the computer, so maybe an external hard drive or a USB stick, we need to be able to mount these and unmount them. Okay, so mounting is when we, and just to put this in Windows context, because I think a lot of people are familiar with Windows, when I stick a USB drive into a Windows machine, it comes up and it's assigned a drive letter. Well, that process is known as mounting. And when I safely remove that disk from the operating system and it tells me I can go ahead and pull it out, that's known as unmounting. So when we unmount something, we are safely removing it. When we mount it, we're putting it into our file system tree so that we can access it. Now, mounting and unmounting happen automatically at the beginning and the end of running the operating system. Let's jump back over here and let's take a look at that file over here. So I'm going to change directory to the etc directory, and then let's just cat out the fstab file. So this is a table, it's a file system table, that's where the file name comes from. And it's just got on each line here an entry for a particular disk drive, right? So it could be a USB stick, could be external hard drive. For the most part, what goes in an FS tab file is like network shares and internal hard disk. So these guys are comments. Anything that starts with a pound sign you can ignore. It's going to be ignored by the system. This identifies the disk by a UUID, tells us where we want to mount it at. So this is actually the root file system. And then we see that it's an ext4 file system, and here's some particular options that we can use with that file system. The only other disk that we have on this system is for swap. So we can see the UUID value, universally unique identifier for that particular disk. It doesn't have a mount point, and this is used for swap. So it's a swap file system. Here's the option for it, just SW. I'm not sure what that means, but we could look that up if we were interested. Okay, let's look at real quick using removable and optical disk. For the most part, desktops environments have made this very easy for us. That process that I just detailed out about Windows, where we plug in a USB stick and it just pops up and works the same in Linux if we're using a GUI. So plug in something and it comes up. It's probably important to note here that if we're dealing with just a text-based user interface, so we're not using a GUI, for the most part, these things don't get automatically mounted like they do when we use the GUI, and we just have to go in there and mount them ourselves. We just use the mount command to do that. Okay, so kind of wrapping up the lecture here, we're going to talk about displays for a second. So I had mentioned that X is our windowing system, so that's what shows us the GUI. So what all steps are involved in managing a display? What needs to take place? We need to initialize a video card and be able to set its resolution, right? If we wanted to change that, make things really big, we could use an 800 by 600, and there's several resolutions in between there. And it also allocates window sections to applications. 1080 alright, you can have this chunk of or this section for your application. It manages overlapping windows, pointers such as the mouse. It even manages like the keyboard as far as directing input to the active application. So like when I click into something like this search box and I start typing, even though this is in Mac, if this was in Linux, it would be the X Windows system that's handling that. It also is used to display text and shapes within windows and provide user elements to move and resize windows. So just really basic things that we're used to in all operating systems. And then it also manages window interiors such as the scroll bars and all of these little widgets that we see in here. So what handles what part of this? We got 8 steps here. The X Windows system handles steps 1 through 6. Alright, so these really low level things. A window manager, which usually comes with our desktop environment, handles step 7. So user elements to move and resize windows. And then the widget sets handle step 8. So all of these buttons and the display field here and the scroll area over here, these are all widgets. Widgets are just little sort of primitive pieces of a window. So there's a few different widget sets out there. QT is a popular one, and GTK is another popular one that you may see mentioned. What about managing displays? In Windows, we always have to install that driver, right? And if we put in a new graphics card, we're going to need a driver in order to let the operating system know how to run that graphics card. Well, the same thing's true in Linux. A lot of drivers are already included. They're built into the kernel, or they're loaded later on as kernel modules. So sometimes things just work when we plug them in, and that's always nice. When they don't work, sometimes we have to use other drivers. So if we have an NVIDIA video hardware or graphics card, we can try the NV driver. We can try this, I think it's pronounced NuView, or we can try the NVIDIA driver. So all of these guys would be kernel modules that we would just load, and once they're loaded, it should hopefully take advantage of that hardware. There's also AMD and ATI video hardware, so we may have to use the ATI kernel module or the FGL-RX kernel module. And then of course there's the Intel video hardware. So if you don't have a graphics card and you have an Intel based processor, you probably have the graphics capability built into the processor, and you're probably using the Intel driver. There's also some generic drivers, FBDEB and VESA. So these guys are generic and they work on a wide variety of hardware, but it is suboptimal because the performance isn't that great. So it could be used for debugging. If you're having problems with your graphics card, you can use one of these drivers just to get you limping along long enough to figure out what your problem is and what driver you should actually be using. And moving outside of the computer, how do we connect display hardware to the motherboard? Well, there's a few standard interfaces, sort of following the evolution of time here. The sort of de facto standard for many years is this video graphics array, or VGA. Then we moved into more of a digital interface, so this is an analog interface. 15 pins. We'll take a look at what the connector looks like in a minute, and I can almost guarantee you've probably seen one before. DVI is the evolution of this, and it's digital, so I'll just underline that there. And HDMI is sort of the evolution of DVI, and actually DVI is a subset of HDMI, in that HDMI is video plus sound, whereas DVI is just video. And of course VGA is also just video. So that's the nice thing about HDMI cables. We can use those. We can hook our TVs up to our sound bars with them. We can take our Xbox and hook it up to a TV. And we don't have to do a separate cable for the sound that comes out of the Xbox as well. So what do these connectors look like? Well, here's a VGA adapter right here, and here is an HDMI connector right here. So definitely look different. Remember, there's 15 pins in here, and then this guy's digital, whereas this guy's analog. Alright, it's also common that we need to configure our resolution when we plug in a new monitor. So, older hardware is going to be a very low resolution. Not a fun experience. Everything's really big, there's not a lot of screen real estate, so typically what we see are these HD resolutions nowadays. So 1920 by 1080, this is known as full HD, and it actually goes up higher now. We have high DPI monitors. A good example of that is the Retina displays used on Macs. And then of course in between we have all sorts of resolutions in between, and some some lower price laptops may not support full HD, so they'll just go to 1280 by 1024 or 1366 by 768 as a way to save money. So Linux often detects the optimum resolution and just uses it. If it doesn't, then we can go into settings and we can click on our displays, and we can change it right here with this drop down. Sort of like going into the control panel in Windows and changing your resolution there. Right, handling USB devices. So these are typically human interface devices, things that a human's going to use, like a keyboard or a mouse. Could also be disk storage. Could also be a mobile phone, camera, ebook reader, music players, uh, tablets, things like that. Could be scanners or printers. So we use these a lot so that we can add extra functionality onto our computer. And for the most part, these guys are plug and play too. Um, it's not included in the slides here, but I just want to show you. We've been talking about all of these ls commands like lspci and lscpu. Well, I keep getting my password wrong. There is an ls command for USB devices too. So sometimes when I plug in a USB device and it's not detected correctly, I'll just run lsusb and make sure that it's seen. So I only have some generic stuff on here, and that's byproduct of using VirtualBox. I don't have anything actually plugged in as a USB device, but we can see what it sees. At least it sees a 2.0 hub, so USB 2.0. It sees a legacy USB 1.0 hub, and then some sort of a VirtualBox USB tablet. So that probably allows for some sort of tablet functionality in the VM. But if I were to plug in like some sort of a USB stick, we would see an entry in here for it, and sometimes that can help us hunt down at least like what it is, and we can do some Google searches on that to try to figure out, why is it not working correctly or showing up or something like that. Okay, so last slide here, managing drivers. I'd mentioned that a lot of drivers are included in the kernel. Sometimes drivers are stored in the library or the application. So where is the driver running? Is it running in the kernel? Is it running as part of the application? Really depends. Depends on the developer and what was needed. As far as locating and installing new drivers, we need to do that when we get new hardware. Definitely when we have unusual hardware that isn't included in the kernel already. Proprietary drivers for sure. So something like high-end video cards, usually we need to install a device driver for that. And a good reason that we want to keep up with new drivers after we install them is bug fixes. So bugs happen, right? If you've taken any programming courses, you've probably realized it's pretty easy to make mistakes. And the more complex software gets, that doesn't change. It's still really easy to make mistakes, and it's hard to find them. So when they do find them, they release updates, and when they release updates, we should be looking for those so that we can install them and not run into these bugs on our machines. Alright, so I think that went probably a little bit longer again than I normally like to, but I hope you got something out of the lecture. Let me know if you have any questions from it. If not, I'll see you guys in the next one. Thank you.